15 is not a calculator question, so this one is fair. um, G is a differentiable function. G of x is less than 0 for all real numbers. When they give you that function, it's straight up AP test question where they give you kind of a general function and not a specific function. So we would factor the first part of that. And then you have this unknown function G of x. But what they do tell you is G of x is always positive. So it's just a little different variation of the problems that we've done over and over and over again all year, where we're going to test this. Excuse me. The points we're testing are -3 and 4. We have a variable term here, but you're told that that doesn't have a 0 because it's always going to be a negative value. Test your numbers. If this plug in a -4, this factor is negative, that factor is negative, this one is always negative. So overall, it's going to be a negative value. If we test 0 in between, this factor is still negative. This one switches to positive, however. This one's always a negative, so this would switch to positive. And if we test a 5, positive, positive, negative, we would see that we get one of each. You're going to get a minimum at -3, and you're going to get a maximum at 4, and that's letter B. 16 is a pretty big one because this can appear in a lot of different ways. Even when we did chapter 7, when talking about the sand coming onto a beach, sand getting removed from a beach, water going into a tank, water going out of a tank. It deals with this idea. When it asks for the absolute maximum and minimum values of your function, first understand we want ultimately functional values. When we start talking about absolute maxes and mins, we would always list where can we get our absolute maxes and mins. One of them that we haven't had yet today or with this packet is at your endpoints. So that's definitely going to play a role in this question. And then our critical points we have dealt with a little today. F prime is 0, F prime being undefined. This is the one that we set up our candidates. So with a free response question, which is what you'd be taking, if you're asked to find an absolute max or a min, this is how you want to approach it. We for sure have candidates at 0 and 3. When we take our derivative, so 3x squared minus a 6x, set that equal to 0, 3x times x minus a 2. 0 is a test point from here, but we've already got that taken care of. We also, though, get a test point at 2. Since we're ultimately looking for values of the function here, we don't really need to do a sign chart. It doesn't really give us any information that would be useful to us to figuring out our functional values. What we did for these is, this is when we just figured out, if these are our 3 candidates, let's just figure out what these values are at those times. So at f of 0 or at x equals 0, plug in a 0 into the original function here. And when we do that, we would get a 1. Take 3, plug that in, you're going to get a 1. And if we take 2, plug that in, we would get -3. Answer the question the way they want us to answer it. The absolute maximum would be the functional value of 1, and the absolute minimum would be the functional value of -3. All right, just give the, it's a -3. Just give your y values. All right. 17. This actually, there is something new here. So 17 is pretty important. You're going to want to make a note of this, write this down for future reference. It is something that pops up here and there, even on the free response portions of some tests. So it's specifically going to deal with number 3. So pay particular attention to that question. 17, let f be a function that is differentiable on the open interval -3 to 7. So this word again, they deliberately give you that word and not this word, continuous. And the reason they don't do that, and this question specifically tests you on this, is you need to know if I am differentiable, that would guarantee that I am continuous. So by saying this is a differentiable function, it is also telling you that you're continuous, and that's going to play a role. It's on an open interval -3 to 7. They're giving you a couple of values. F of -1 is 4. F of 2 is -5. F of 6 is 8. So I'm going to approach this initially graphically. So let me draw this graph in. What you're told is -1, 4. lies on our graph. 2 negative 5, so 2 would be over here somewhere, and then negative 5 is down here. That's on our graph. And then 6, 8. So here is 6, and then 8 would definitely be above the 4. So we'll say that's 8. All right. We have a continuous graph and a differentiable graph. So if you look at number one is asking you, does there have to be at least 2 zeros? Well, that's directly testing you on this idea now, knowing that we are continuous because you are differentiable. If I have to get from this point to this point to this point, there is no way I could not cross the x-axis at least twice. I have to go from positive to negative and then negative to positive. So I know for certain that there are at least 2 zeros. There could be more than 2 zeros. We don't necessarily know that we don't cross the x-axis more than once in between a negative 1 and 2, and then again between 2 and 6, but there's at least 2. So number 1 is definitely true. So we can get rid of this. We can get rid of this. Number 2, f has a minimum at x equals 2. Well, the way that I just kind of dotted this in and I graphed this very lightly, yeah, this would be our minimum, but that doesn't necessarily mean that's what really happens. There's nothing saying that our graph couldn't have done this, that we decreased, came down here, and then we passed through this point. Now this here, this point would be our minimum point. X equals 2 would not necessarily be a minimum. So that does not have to be true. And if we know that number 1 is true, we really didn't even have to worry about number 2 because there wasn't any of these that combined 1 and 2 together. So 2 is definitely one we're not considering. Number 3, so make a little note of this. There is a little theorem. We usually deal with it a little bit more at one of the reviews. It's called the intermediate value theorem. So you want to get that down. You want to kind of understand that this does appear randomly on some free response questions. And it's similar to number 1. The intermediate value theorem is also going to be could hold true for number 1 or be applied to number 1. This is now saying between 2 and 6. So here's 2. Here is 6. Do we have to have a functional value somewhere in between 2 and 6 that would equal a 4? And then here's the functional value of 4. So what the intermediate value theorem tells you is that if you're continuous, which we are, so over here again, make even more emphasis on this, if you are continuous, you have to hit every functional value from the lowest to the highest. So if I know that here's my value at 2, here is my value at 6, there is no way I could have skipped over this value at 4. That's the intermediate value theorem. It's really logic. It's really just, you really don't even have to really think about it much, but there is a fancy name for it. It's called the intermediate value theorem. So number 3 has to be true. So we know A is not the answer. Number 4, we referred to this in that first review. Whenever you start talking about something being differentiable and continuous, and they say must be true or false, they start talking about the true statements of functions that are continuous and differentiable, and you're starting to give intervals, the mean value theorem is almost always going to pop up. That's what number 4 is testing you on, the mean value theorem. So we're going to do it between 2 and 6. So if I did f of 6 minus f of 2 over 6 minus the 2, f of 6 would have been 8. F of 2 would have been a negative 5 over 4. What we find is our average rate of change is 13/4. Since we are continuous and differentiable, the mean value theorem is guaranteed to be true. The mean value theorem says whatever your average rate of change is, which we just showed is 3/4, that somewhere the instantaneous rate of change would also have to equal 13/4. So this would have to be a true statement, which means E is our answer. Okay, 18, which of the following statements is true? For this one, I like this one too because it brings back one of the things that we haven't dealt with a whole lot today. If I have this function It says the function is always increasing except at x equals 0. So the idea of increasing we can figure out by our derivative. So we would get 1/3 x to the negative 2/3. Set that equal to 0. Let's simplify it. All right, so that's what that derivative would simplify to be. Actually not. Should be x squared. So it's 1/3, and then the cube root of x squared in your denominator. If we want to be increasing, so the first time I think we've had to worry about this, our critical points are when the first derivative equals 0, so we have it set equal to 0, and then also when your first derivative is undefined, so don't forget that. Our derivative in this case is undefined at 0. If we try to solve this equation, so if you multiplied both sides by that cube root of x squared, what you would get is just a 0 on the left still, but you would now get equal to 1/3. Since those are not true, that tells us we don't get another test point. So only test point is 0. If we look at this derivative here, our numerator is always a positive 1. So my numerator is always positive. My denominator will also always be positive because 3 is positive. Any number I plug in for x, I'm going to square. That's going to be positive. So what that tells us is our derivative is always positive. So that makes number 1 true. Your function is always increasing because we have a positive derivative value everywhere except at 0 where we're undefined. So number 1 is true. 2, the tangent to the curve at x equals 0 is horizontal. That is false. Horizontal means our slope would have equaled 0 there. Our slope is not 0 at this x value. Our slope is undefined. So that means there's probably a sharp corner or a vertical tangent at that graph, but there's definitely not a nice slope of 0 there. Nowhere does our slope equal 0 because over here, this equation didn't produce any answers. And then number 3, the mean value theorem can be applied to our function from a -1 to 1. That is also going to be false. If you reference again back up to number 17, we have to be differentiable and continuous for us to apply the mean value theorem. This function is not differentiable at x equals 0. So the mean value theorem cannot be applied because within this interval is the x value of 0, and at x equals 0, the derivative is undefined. So our only answer there is 1. Okay, 18. Just pay particular attention to the way this is worded. You are given a velocity, and they want to know when is the acceleration a minimum. So whatever I want to minimize, it would be where that derivative is equal to 0. So if I want to minimize my acceleration, what I really want to know is when is the acceleration's derivative going to change from negative to positive. So if that's your velocity, the first derivative of that particular equation is the acceleration. But that's what we're trying to minimize. So I actually want the derivative of the acceleration. Set that equal to 0. Let's pull out a 3t. Yeah, let's do -3t. So that would leave you with 2t minus, 2 minus 9t. I think, let me check that. So -3, 6, 27. Yeah. So then testing 0, and really we can't go past the time of 0, so that's an endpoint. We test 2/9. If I plug in a 1/9, this factor would be negative. 2 minus 9 times 1/9 would be 2 minus a 1. That is positive. So overall, this interval is negative. If we plug in, let's say 10, this factor is always a negative. They're going to be negative if I plug in a 10, and then 2 minus 90 is negative. So change this guy to negative. Overall, we are positive. 2/9 then is our minimum. All right, moving along. Find k so that the relative minimum of this function occurs at x equals 1. So they're making you go backwards. They're actually telling you where you have a minimum. Our minimum is at 1. So what that would be telling us is that 1 is either an endpoint, it's where our derivative is 0, or it's where our derivative is undefined. We're not given any endpoints, so that really just leaves us with the idea that if I took the derivative of this, so we get 3x squared minus 1 over k plus x, and then times the derivative of k plus x. K is a constant, so it would go away. The derivative of x would be a 1. So what this is telling us pretty much is that if we're going to have a minimum at this point, what that would tell us is if I let x be a 1, that this either makes this undefined, the k value that makes it undefined, or the k value that makes it 0. So there is a k value that would make this undefined. K cannot equal a -1, so that would be a potential answer. But if you look at our choices, none of that choice is not listed amongst our choices. So we don't have to worry about that. So the only other option would mean when x is a 1, if I have a minimum, that means my derivative here would have to have a value of 0. You have an equation now. We can solve this. I'm going to add over that fraction. That would now just be equal to 3. Multiply your k plus a 1 over. So we would get, do this over here, 1 equals 3k plus 3. All right, solve that. So subtract the 2 over, divide by 3. Should get -2/3. Okay. All right, tables and graphs. Big opportunity here for this to be on the AP test. This is actually an old AP question. I think all of these are old free response questions that you're going to want to be able to handle pretty well. So 21, it says the function f is continuous on a closed interval, so that's important to know this is closed. The function is twice differentiable at -2 and 3, and the function has derivatives with the properties shown below. So a setup that we've done many times. Hey, this is opening your interval now. What that's telling you is don't worry about your endpoints. Your endpoints are always a maximum or a minimum, a relative max or a relative min. If they made this a closed interval, this is a little trickier question, but right now they're leaving that open. We don't have to worry about our endpoints. So if we want to know the x coordinates where f has a max, then what we would want to find is when does f prime change from positive to negative? And really, that's our justification. When you justify these free response questions, or when you have to justify it, the whole test is free response questions, so it's going to be a matter of time before you have to justify something. Be specific. So say f prime is changing from positive to negative. Okay, don't say the curve, the graph, the slope. What's changing from positive to negative, specifically f prime. So that is our justification. Then we just have to figure out where that happens. So go to your f prime row, figure out where you go from positive to negative. All right, that would be at the x value of 0. If we just kind of follow along into this row, all right, that's when we're going to be going negative. All right, so we would say at x equals 0, and it's because f prime is changing from positive values to negative values. B, when does our graph have a point of inflection? So that was going to be, in terms of justifying, when f double prime changes signs. So we go to the f double prime row here, and we want to figure out where we have a sign change. Right off the bat, we get one. We go from positive to negative at x equals a -2. We go again from negative to positive at the x value of a -1. Here we don't get one. We went positive, positive, but then we'll get another one here when we go positive to negative, and that's at 1. This is ultimately your justification. F prime is changing signs at those values. C, find where the graph of G has a relative maximum. So if G is what we're trying to maximize, it would be where G primed changes from positive to negative. So that right there is your justification. Now we just have to figure out where that happens. We did our derivatives in the previous packet, so we would hopefully be able to look at this function now, take the derivative of G, and know that G is really just f of x. So now we're looking at this row, and we're looking to see where does G primed, which is really f of x, go from positive to negative. If we follow through here, that doesn't happen at all. So you would say none. And then you would say because g prime never, I have to add a little here, but you're bright enough to know that and you can do it your own. Because g double prime does not change from positive to negative. So there would not be a maximum in this one. And then D, last but not least, where does G have a point of inflection? So that's going to be where G double prime changes signs. So if we come up here, here was the derivative of G. That gives us G primed. We now need G double prime. So if I now took the derivative of this, G double primed of X would be equal to F primed of X. So we're looking back at the F prime row here. Now we just need any sign change. So we get one right away at X equals -2. At that value, we're going from negative to positive. The next one we won't. We go positive, positive. But the next time we will. We go positive to negative. That happens at 0. And then the next one we do not. We go negative to negative in that row. So those are our 2 points of inflection for G. Graphs, really, really common. If I were to tell you that we were doing 6 pre-response questions, still they always give you, almost always give you some sort of a derivative graph that you have to kind of play around with and manipulate. Plus, I just want to go over these explanations just so we're clear on what we're writing. The figure above shows the graph of f prime, derivative of some function f between -7, +7. Notice how this is a closed interval initially. The graph of f prime has horizontal tangents at -3, 2, and then 5, and a vertical tangent at x equals 3. I'm not sure if I may have given you this one before, I'm not sure. Either way, letter A. Notice how, again, they open this up. If they hadn't opened that, your endpoints are going to be a maximum or a minimum, and we need to understand which one of those two they are. We'll talk about that, review that here in letter D. Right now, this is easy. Where does f have a minimum? It's going to be when f prime changes from negative to positive. So we look up here at our graph. F prime is changing from negative to positive at the x value of a -1. The max you're looking for when f prime, whoa, what did I do here? Negative to positive. F prime for a max needs to be changing from positive to negative. That happens at 5 or -5. So our answer to this one is -5. C, find all values of x where the second derivative is less than 0. If this is your first derivative and we want the second derivative, the way we take the derivative of a graph is the slope, and we want our slope to be negative. So when we look at this graph, we have negative slopes in here. We have negative slopes kind of in here. So this is now the trick of this one. You would go from, let me move this up just a little bit, definitely -7 to -3, and then a union. Let me cover this up so I don't congest this. Starting at 2, but what you want to be careful of, we don't want to say from 2 through 5. We want our second derivative, or the slope of the graph we are looking at, the slope of f prime, to be negative. When you were told that you have a vertical tangent at 3, what that means is at 3 here, our graph is going straight up and down for that one moment, so it wouldn't have a negative derivative, it would have an undefined derivative. So we'd have to stop at 3, leave that open, pick back up at 3 until 5. All right. D, now we're considering our endpoints. So the way that I had you do this is still a pretty effective way to go through this, is to sketch out what our original graph would look like. So initially, f prime is greater than 0 here. It's above the x-axis. So we would be increasing from a -7 to -5. So a -7 is a minimum. So if the endpoints were included, that would have been an answer down here in letter A. And again, the only reason it wasn't is they didn't include them in the setup. Then our derivative goes negative, so then we're decreasing here. Our derivative graph is below the x-axis until a -1. So then we decrease until we hit -1. After a -1, our derivative is pretty much positive this whole time. So we're increasing the rest of the way. When we hit 5, we flatten out momentarily because our derivative has a value of 0, but then we continue to increase until the very end. So we end up having two maxes, the one that we've already identified here at -5, and the second endpoint is a max, and then we have two minimums. This one we had already talked about in letter A. We found this endpoint was also a minimum. So what we now have, at what value in here does f obtain its maximum, absolute maximum value? It would have had to have been at the x value of 7. All right. All right. Yeah. All right, 23. Unlikely you'd have to deal with this, but again, the graphs are important. Let f of x equal this, the integral of h of t from a to x, which of the following is f? So what that would basically tell you, so let's take f. If I took the derivative of f, sorry, this is h, isn't it? The derivative of f, the derivative of the integral would cancel. It would just leave us with h of x. So when they tell you that this is the graph of f, this is the graph of h, is shown below. What we've just shown here is h is really your derivative graph. So h is f prime. Then it gets a little easier. We would then know that this guy right here has to be a minimum because f prime is changing from negative to positive. So the graphs that have minimums would be A at the point B. Definitely not B. We might lose some of these. This has a minimum, so it could be C. D has a minimum at B. If you scroll on down to E, you'll see letter B does not have a minimum, or letter E does not have a minimum at B. So it's not A, it's not E, but it could be A, it could be C, and it could be D. The way we can distinguish between those is at this point right here, if I ask you what is f primed of B, since we're crossing the x-axis, the derivative value would be 0. If you look at our three possible answers, D is the only one that has a nice horizontal tangent line. That would indicate our slope is 0 there. Here our derivative would be undefined. Here is another sharp corner. The derivative there would be undefined, so it's got to be D. Okay. All right, 24, again, unlikely you're going to get a multiple choice version of this. I'll leave you that. I think you're going to be fine with this. Should get E. We're going to move along here. I think there's one more. Very, very strong chance that this is a question you would receive some component of this. Like I said earlier, these are almost always on the AP test. Oops, do not want to do that. So number 4 says that f be a function defined in the closed interval -3 to 4. F of 0 is 3. And then the graph of f prime, the derivative of f consists of one line segment in a semicircle shown above. All right, so it starts easy enough. A, on what interval is your function increasing? So if this is our derivative, we would want to know in terms of justifying this, so I'll do this all at once, that we want our derivative to be positive. This is your derivative graph. They tell you this is f prime. So we would be positive when that graph that we are looking at, f prime is above the x-axis. So in this interval, we would go -3 to -2. That's when f prime is positive. B, find the x-coordinate of each point of inflection of the graph of f on the open interval -3 to 4. Justify your answer. So this question, I don't know what year it was. What's it say? Okay, it doesn't give you the year, but I do know when my kids came back this year, they all got one of them, and then only about half of them got the second one. There are two answers here. So a point of inflection, so make this clear. And the reason all of them got one of them is they all understood f prime, the idea that f prime needs to equal 0. Well, specifically what happens, or needs to happen, is the second derivative needs to change signs. So if that is the first derivative, the second derivative is the slope of the graph that we are given to work with, f prime. So the one answer that everybody got was at x equals 2, because they went to this point they understood that the slope here, which is the second derivative, was a value of 0. And then specifically, we had a positive slope of f prime to the left, and we had a negative slope of f prime to the right. So that would guarantee that we have a point of inflection. That would be our justification. F double prime changes signs. You wouldn't want to just say f double prime equals 0 for your justification, because we can definitely, we've shown that a few times in this packet, we can get a second derivative value of 0 but not get a sign change. Okay, so this is our justification, and at x equals 2, that's definitely one of our answers. But there is one more. We can also get a point of inflection. We really just need a sign change. Think about where we get critical points. It's when our derivatives are 0, or when our derivatives, in this case the second derivative, would be undefined. So if we look right here at what would be the x value of 0, pay attention to your slope to the left and to the right. To the left of 0, the slope of f prime would be negative, but immediately to the right, the slope of f prime would be positive. What that would tell us is x equals the value of 0 is also a point of inflection, because our second derivative, you know what? That's not enough to kind of justify this. It's one of the reasons I want to do this, so let me not screw you up. That's what we're looking for, where f double prime changes signs. When they ask you to justify or explain something, you need to always reference the graph that you're given to work with. So we are given the graph of f prime to work with. We were not given f double prime to work with. So we can't say f double prime changes signs, even though that's what we're looking for. So let me not lead you down the path of darkness here. So let's not put that as our justification. We have to reference f primed. So what we're looking for is the slope of f prime changes signs, okay, at x equals 2 and x equals 0, okay? See, they get creative with these. We did a bunch of those in review packet number 3, the equation of a line tangent. It always comes down to a point and a slope. You were given your point. All we really need is our slope. The slope is, again, our derivative value. So let me try to keep this separate. The derivative value at the x coordinate that you are given in your point. In this case, it's the derivative value at 0. So if we look at our graph up here, this is the derivative value. This is the derivative graph anyway. So if I want to know what is f primed of 0, that means I'm going to go to the x value of 0 here, and I want to know what is f prime's value, and at this point, its value would be a -2. Don't think that that derivative is undefined. The second derivative is undefined there. The first derivative value is a -2. So we use those two things, write the equation of your line, and then that's the answer to C. All right, D, tricky, 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 and annoying, messy. So, like I mentioned earlier, they will never give you, in the setup of the problem, something that you would never use. So if we go back to number 4, notice how we have not used this yet. This is one of the ones where when we did these in class, when we did these, we would have marked that at the x value of 0 here, we already had a y position of 3. So it's one of the ones where the idea is at the x value of 0, we know our y value is 3. That's this up here. You were given that. Then the question is asking you, all right, well, let's go 4 seconds later, since we want f of 4, what is our new y value? So the way we have to calculate that, what we need to figure out, the missing element to this question is, what was our change in y over the interval of 0 to 4? Whatever that is, we would add to 3. So the way we would calculate that, the way we would set this up, is we're going to take the initial value that we know of 3, and we need to add the change in y. Well, all you're given with to work with is f prime. So to find the change in y from f prime, we'd have to integrate f prime, and we'd be integrating it over the interval of 0 to 4. To integrate a graph, that's what we get into in our next review, but it'd be a good precursor here. We find the area enclosed by the graph and the x-axis. So to find the integral of 0 to 4, what we need to find is this area in here. So what we would have to basically do, and it's kind of ugly, to find that, we're going to find the area of this overall rectangle here, which is pretty easy. It's a rectangle with a base of 4 and then a height of 2, so that would be 8, minus the area inside, or I'm sorry, the area of the circle. If we want the stuff in between the rectangle and the circle, we'd have to subtract the area of what would ultimately be a semicircle. So we would do 1/2 pi, and then the radius of that circle that we would square, the radius would have been 2. So 3 plus, and then we would do 8 minus 2 pi. That's kind of our answer. What's even trickier about this thing is all of this area is underneath the x-axis. So whatever area it has, the value of that would have to be negative. So that our final answer would be 2 pi, and then 3 minus an 8 would be a -5. All right, pretty tricky stuff. Letter D, second part, this one, it asks you to go backwards now. So what this is saying is at the x value of a -3, we don't know the y value, but we do know at 0, our y value was the 3 that they gave us. So it's similar in the sense that we want to find the area of these. So let's go ahead and find the area. This triangle here now, since we're going to go backwards, has an area of 2, but it's underneath the x-axis. So this has an area of a -2 right here. So you just can think in your head, all right, well, what was my value at a -2 if I decreased by 2 and I ended up with a value of 3? That would have been 5. But we need to go back to the 3 here. This has an area of 1/2. And we had to go from a -3 to -2. We would have increased by a 1/2 to get to 5. So what that would have meant is our value here would have had to have been 4.5. So that would be our answer here. So there's really now 2 different ways we could approach this. You can still say, that'll work actually. So if you just look at your graph and work backwards, that's totally fine. If they ask, if we wanted to set this up, we could still do 3 plus, and then what we would be doing is the initial value that I know is 0. All right, that's what we were given here. At the x value of 0 is 3. And then we would go to the -3. What that would require us to do then is, well, before that, we could flip our limits so that it looks normal, -3 to 0. And then when we flip our limits, we're going to be subtracting, which is now the other way to do this. Take your 3, and then now let's subtract away the change that we would have had from the beginning to the 0 that we knew. All 3 of these options would work in terms of giving you that 4.5. Okay, mercifully, this is all over. Again, this is the longest one, I promise. They don't get any longer than this. Pretty critical though, and even that question, hopefully D, you understood a little bit. Spend some time with it, see if you can figure it out. Pretty common question, something that I wouldn't be surprised if you see here next month when you sit down to take that. If you have any questions, let me know. Hope everybody's well. So test review number 3 was a huge part of first semester. It was the trying to find maximums, minimums, increasing, decreasing, when does a function do all those things. It would have been a huge part of the AP test. It's a huge part of the AP curriculum. Certainly going to be something that you're going to want to know pretty well. This is, as a little heads up, one of our longest ones. Usually our AP review sessions in the evening are anywhere from an hour to an hour and a half, and it's this one that is the longest. So just a little heads up. I am going to try skip through this a little bit. I will leave you the answers since you're at home anyway with plenty of time to spare. The ones that maybe aren't quite as critical, or once we've done one or two that are pretty similar, I'll just give you the answers, and then you can kind of look through, see if you can get it yourself without having to sit in front of the computer listening to me the whole time. So to start with, the first thing that we did, or one of the big things that we did in this chapter, were the related rate problems. That's what these are. These are what we're beginning with. So we set up, the whole idea of understanding this as a sphere. It's expanding at a rate of 60 pi, then you would see this inches cubed per second. So when we would see this inches cubed per second, that would have given us the idea that this is the change in volume over the change in time, and that was 60. Question then was how fast. We're also talking about the volume. When we look at this, volume of a sphere. So we know we're going to have to use the volume of a sphere, which is 4/3 pi r cubed. And the question is how fast is the surface area expanding? So what we're looking for is the change in surface area with respect to time. Also tells us we're going to need the surface area of a sphere when the radius is 4. So we're looking for that, and then the radius is going to be 4 inches. These are very common. There won't be, especially for you guys, no way they're going to build a full free response question around this type of idea. But a lot of times it's kind of like a B or a C when you're in an AP question. And they usually keep it fairly simple, but the most common is when you're given two different formulas. So we have a volume, we have a surface area, we got to be able to work back and forth between them. Since this question is ultimately asking you for this here, the change in surface area, we would first go to this one and take the derivative of this with respect to time. That would give us the change in surface area over the change in time. Over here we take our derivative, we get 8 pi r, and then that would be the change in the radius with respect to time. If this is what we are looking for, then what we would need to know is our radius and the rate of change of our radius. The radius we know, you were given that over here. So that we're going to throw in our 4 inches. But we still need to figure out what is the dRdt. Like this, we don't know yet. We get that from our other formula. These free response questions, they'll never give you anything that you're not supposed to use at some point. So that's why you were given this information, the change in volume. So take the derivative of the volume equation with respect to time. So we would get dV over dt would equal 4 pi r squared dRdt. dRdt is what we're trying to solve for, but now we've created this dV dt here, and we can then use this value to substitute in for that. So this would become 60. 4 pi, our radius we know was 4 squared, and then we can solve for dRdt. I've run out of room again. This pen is very large. If we solve for dRdt, then we're going to plug that in over here. So this is what, 1664 pi. And this should be 60 pi now that I'm looking at it. So when you take, 60 divided by 64, this should end up being 15 over 16. Plug that in. Simplify. This would be 30 pi. If this is free response, which again, pretty commonly an element of this is, they would almost certainly ask you for your units. This is the change in surface area with respect to time. So for us, that would be inches squared. That's our change in area squared with respect to time, which is getting measured in seconds. So that was our related rate problems. These all followed similar ideas. Most common type is that where you got to work back and forth between two separate equations. You'll also see these a lot of times with angles, and that's what number 2 is. This is an old question that we've done before. I think I actually put this on your test, whether you remember that or not. Says a balloon is rising straight up from a level field. So over here, we'll draw this. Here goes our balloon. It tells you it's going straight up. It is tracked by from point A 500 feet away from the point of liftoff. So this is going to be A. We know the length from A to the point of liftoff is 500 feet. When the angle of elevation to A, or from A to the balloon, is pi over 4, so this is our balloon, we'll call that B. And when the angle of elevation from A to the balloon, so this is our angle that we're talking about, when that angle is 45 degrees, so pi over 4, the angle is increasing at a rate of 0.14 radians per minute. So then we'd say d theta dt is 0.14 radians per minute. And then the question is, how fast is the balloon rising at this time? So we're looking for how quickly is this going up. So we are looking for dB over dt. So anytime we're dealing with the right triangle, you're going to be dealing with either SOHCAHTOA or the Pythagorean theorem. Since this one is involving an angle here, this theta, which is going to be the pi over the 4, it's got to be a trig function. If we look at our angle, our reference angle, we're dealing with the opposite side of B, the adjacent side of 500. So that sets up our tangent of our angle is equal to the opposite side, which is the balloon, over the adjacent side, which we call A. One of the things you want to remember is that if any of these are constant, and if any of our variables are constant, either the theta, the B, or the A, then we can plug them in right away. That would have been true up in number 1 as well. I should have mentioned that. It just didn't pop up in number 1, so we didn't necessarily have to talk about it. But in this one, we do have a constant. And that constant value, if our balloon is always going straight up, and then we have somebody just tracking in here from point A, this horizontal distance would never be changing. So what that allows us to do is to go to A and plug in that value. We don't need the derivative of it because it doesn't have a rate of change. So that's something that will make this a little bit easier if we can recognize that. I would then solve for B, so multiply that 500 over 500 tangent of theta. Now take our derivative of this with respect to time. This will give us the dB dt. That's our answer. That's what we're trying to find. We would get 500. Derivative of tangent is secant squared of theta, and then d theta dt. So our answer would be 500. And then what we would have to figure out is what is the secant of theta. Oops. And in this case, we know what our theta is, and we try to write this again. Okay, go away. So let's try this again. So 500 times the secant of pi over 4, and it was a secant squared, so whatever this gives us, we need to square, multiplied by the d theta over dt, which we were given as 0.14. That would be our answer, dB over dt. Okay. So if we were to evaluate that and simplify that, what that should give us then is 140. And then since this is the change in the balloon's length, change in the length of B over our change in time, it would be 140 feet per minute. All right. All right, number 3, 2 cars leave the airport at the same time, traveling in separate directions. Their courses diverge by 90 degrees. Car A travels at 50 miles per hour. Car B is traveling at an average rate of 60 miles per hour. How fast are they? How fast is the distance between them changing? So, what direction are we going? Yeah, it doesn't really say. So here, let's say this is our airport. Let's say this is car A. Let's say this is car B. We're told that they're diverging by 90 degrees. What we are looking for then, if these are the cars here and here, is D. How fast is that changing? So it's another right triangle. We do a squared plus b squared equals d squared. Take our derivative, 2a, and then dA dt plus 2b dB dt. And then that would equal 2d times 2d dt. When we did these, we talked about how since all of them have a 2 in it, If we don't really even want to show those, we don't need to. So get rid of those. I don't know why it does that. Sorry. I've started to really hate erasing because now it always does this. Get rid of this. Get rid of this. And then now we just plug in the values that we know. You were told that car A is traveling 50 miles per hour. So we know that dA dt here is 50. You were told that car B is traveling 60 miles per hour. So dB dt is 60. If we are looking ultimately for dd dt, then we better be able to figure out what's A, what's B, what's D, so that we can then figure out dd over dt. You were told they were traveling these rates for 2 hours. So if car A was traveling 50 miles per hour for 2 hours, he would have traveled 100 miles. Car B is traveling 60 miles per hour for these 2 hours. So he would have traveled 120. The missing element that we don't know is D, but we can do our Pythagorean theorem. We know it was 100 miles squared plus 120 miles squared would have to equal our D squared. We could then solve that. That would be, don't round this. This is me being not good with the rounding, but this is the key that I have from many years ago, and it'll get you close enough. This is 156.2. When we now solve this, what we would get is dd over dt is equal to 78.1, and then this would be miles per hour. It's miles per hour. All right. Okay, next one, I'm going to switch over to the PDF because this I had to do some copying and pasting. So give me a minute. PDFs don't usually format very well. So let me get this up. This was an old free response question on this, just as a heads up. So they did, when they had this question, they were given the shape, the graph. So they gave them a square and then they gave them a circle that was inscribed in the square. So as best we can, we'll draw that in like so. That's the first sentence. Second sentence, the circumference of the circle is increasing at a constant rate of 6 inches per second. So that's our circumference, constant rate 6 inches per second. So that gives us dc over dt, and that is 6 inches per second. As the circle expands, the square is expanding as well. So the circle is getting bigger, but the square is going to expand, so that basically this always looks like that graph there. Pretty simple little setup. And then A, find the rate at which the perimeter of the square. So we're looking for the rate of the perimeter of our square. So we're going to be looking for dp over dt. That's the answer to part A. And then, like I said earlier, they're going to want units with these questions. So there's really a couple ways to approach this. Since the square and the circle are tied hand in hand, the way that we're going to approach this is we're going to define this here as our radius of r. And then since we want to really keep the same variable throughout, we don't want to have to work back and forth. If we're going to call that r, we're going to let each side of the square be twice r. The reason we need that, if what we're looking for is the rate and the perimeter of the square, we always have to come up with our own equation. Here you really did need to come up with it yourself. It wasn't a simple Pythagorean theorem. It wasn't a geometric series shape. If you want the rate at which the perimeter of the square is changing, so we wanted this over here, we first and foremost better be able to come up with the perimeter formula for this square. So by defining r as the radius of our circle, we can now say that the length of all the sides is twice r, so that we know the perimeter of our square right now is 8r. Once we have that, then we can go through. That would have been the hard part. This is a pretty straightforward step. Take the derivative, drop the r. The derivative of r would be dr over dt. dp dt is what we're trying to find. So that would be 8 multiplied by dr dt. you were given the circumference rate of change. So we don't want to be plugging that in. So what that would mean is we probably, like the first one we did, got to deal with our circumference. And in order to use dc dt, we're going to take the derivative of this, which would be dc dt, and then drop our 2 pi. The derivative of r is dr dt. If we can solve for this dr dt, we can then plug it in over here, answer our question. So dc dt, that's why you were given that. This was 6 equals 2 pi and then dr dt. So dr over dt would be, divide this here by 2 pi, 3 over pi. Plug that in. And dp dt should be 24 divided by pi. They wanted units here. This is our perimeter with respect to time. Perimeter is a single dimension. There's no squaring, cubing, or anything. So it would be inches per second. All right. B, at the instant when the area of the circle was 25 square inches. So then you were given now that our area is 25 pi inches squared. Find the rate of increase in the area enclosed between the circle and the square. So again, we have to come up with this formula. Once we know that formula, you're going to take the derivative of this and you'll get dA over dt. That is the answer to the question. Find the rate of change in the area of this, but we have to come up with that ourselves. So they're looking for this area here. That's what we're trying to figure out the rate of change of, the area between the two geometric shapes. So if we were to write an area equation for that, what we would want to do is take the area of the square, subtract away the area of the circle. So the area of a square would be the base times our height, so 4r squared. The area of a circle would be pi r squared. That's 4. Once we have that, then we can go through with our work, take the derivative, 8r dr dt minus 2 pi r dr dt. We're looking for dA dt, so in order to answer this, we would need to know a radius. We need to know the rate of change of the radius. They don't give you the radius, but what they do tell you is that the area of our circle was 25 pi. You can set it up as an equation if you want, but you're all pretty bright kids. If the area is 25 pi, that would have told us that our radius was 5. So we let our radii be 5 in those two spots. And then dr dt is the answer to our previous question up here. 3 over pi. So we got 120 over pi minus 30. These pi's would cancel. That's our answer, our unit. Now this is area with respect to time. So this would be inches squared per seconds. Okay. Let me switch back to the Word version here. A little easier to work with. All right. Oh, crap. What is this now? All right. If you go to the next page, you'll see something called Rolle's theorem. I wouldn't even worry about that now. No chance they're going to do that. It's really just a little variation of the mean value theorem. We dealt with the mean value theorem earlier with the reviews and such, so I would not spend too much time on that. But really the next handful of pages are all the, again, old types of problems that dealt with these ideas. First derivative test, second derivative test, and what all that entails. So the idea if a derivative is increasing, that or positive, that means your function is increasing. Whenever your derivative is 0, we call those critical points. That's also when the derivative is undefined. But definitely when it's a 0, we're either going to get a max, a min, or a point of inflection. There's only 3 things that could happen. If our derivative is if our derivative is negative, then your function is going to be decreasing. Second derivative info. Second derivative means the function itself is concave up. It would also tell you that the first derivative is increasing. If the second derivative is negative, that means your function is concave down, telling us our first derivative would be decreasing. And if the second derivative is equal to 0, that means a point of inflection would probably exist. Always need to check for a sign change. So if we took our derivative, just to show that, don't assume this. If we want a point of inflection, we would go to our second derivative. factor that, pull out 20x squared, be left with a 3 minus an x. And then when we test that, we need to make sure that we are getting a sign change. So 0 and 3 would be our critical points. That's what we're testing with our second derivative here. But when we do our sign change and we test all of these, what you would find is we'd be positive to the left of the 0, positive to the right of 0. We would be negative to the right of 3. So what you're going to find is 0, we don't get a sign change. So this is not going to be a point of inflection, whereas in 3, we are going from positive second derivative values to negative second derivative values. So we only have the one point of inflection, it would be at 3. All right. Number 6, determining where we'll just knock out a bunch of these right now, just with one problem. If we want a function to be increasing or decreasing, that's the first derivative. So we would take our first derivative, 12x squared or cubed plus 24x squared minus 36x, set that equal to 0. Pull out a 12x, and be left with what? X squared plus 2x minus 3. Factor a little more. All right, x plus 3x minus 1. Test points here end up being negative 3 and 1. So we test our first derivative values here. This will go what? Negative 4 would be negative, negative, negative. So this should go negative, positive, negative. So where if we're looking for increasing, wherever the first derivative is positive, so in this case from a negative 3 to 1, that's where our function is increasing. Our function would be decreasing from a negative infinity to negative 3, as well as from 1 to infinity. C and D is your concavity. That would be our second derivative. So if we took the second derivative, 36x squared plus 48x minus 36, set that equal to 0, we can pull out, did I mess this up? Okay, never mind, I'm losing my mind. You may not realize this, I just took 10 minutes off to figure out how the hell I screwed this up. And I didn't really read the problem. All we want in C is a max and a min. So there's no need for this second derivative nonsense. We've already done the work for it. Over here, we get a max when our first derivative goes from positive to negative. So that's going to be at the negative or at the positive 1. And then we're going to get a minimum when our first derivative goes from negative to positive. That's happening over here at negative 3. All right, forgive me. 7 and 8. Not really going to do those. As you're going to find out, we're going to talk about this on Thursday. If not, I'll try and record it for those who don't get to join us. There is no specific calculator questions on the AP test. You should be able to do all of these things without having to do it. So we're not necessarily going to do 7 and 8. These really require you to graph and then be able to look at a graph. We're going to do some graph work later in this packet for you to look at a graph, a derivative, second derivative, and answer all those questions. So I don't think you're losing anything by not doing 7 and 8. So to shorten that up a little bit, we will move along, not worry about those two guys. If you are really bored and want some stuff to do, here's your answer to this one. We'd be decreasing from a negative infinity to 2.351. That's number 7. And then number 8, we would be concave out from 0.055 to infinity. All right, if you want to try it. 9 though is non-calculator, so this one should be one that you would be able to do. Where is our function, f of x, increasing at? So that just means our first derivative needs to be greater than 0. So we're going to take our derivative. Requires us to remember our product rule and some, different rules, power rule, exponential rule. So this is our first term. That's our second term. So the derivative of the first is just 2x. Leave the e to the negative x alone. Then we would leave the first term alone. The derivative of e to the x would be itself times a negative 1. So let's change this then to a negative. All right. We want to clean this up a little bit. Set that equal to 0 at the same time. So we're going to get 2x e to the negative x. And then we would get what? Minus x squared e to a negative x plus 3e to the negative x. Set that equal to 0. We're going to go ahead and plug or pull out our common factor of e to a negative x. That leaves you with a 2x minus x squared plus 3, and then the order's kind of messed up, so we're going to do that in the next step. E to a negative x. Let's rearrange this. At the same time, notice how the x squared is a negative. So at the same time, let's make this e a negative. So we're going to pull out the negative so that we have a positive x squared, a negative 2x, and a negative 3. So finally, we have a negative e to a negative x, and then x minus 3, x plus 1. That's our factored version. Our test points then, nowhere is this undefined, so we don't have to worry about any derivative values that are undefined. We're going to definitely test negative 1, then we're definitely going to test 3, and then we need to talk about this. Exponential functions never cross the x-axis. So even though there's a variable here, unless there's a vertical shift, which there isn't in this case, this should never cross the x-axis, meaning this is never going to produce a 0, even though there's a variable x there. So there is no other test point that we're testing with our first derivative. The other thing that you need to keep in mind, when we now go to do our sign change, let's do this first one. Let's say I take a negative 2 and I plug it in. I know a negative 2 plugged in here would be negative. I know a negative 2 plugged into the last factor is going to be negative. But if you remember, the exponential function itself is always going to be a positive value. But since this has a negative in front of it, that tells us that this factor here will always spit out a negative value. So at this negative 2, this one's always negative. This factor would be negative. This factor would be negative. So it tells us that in that interval, the overall first derivative value would be negative. If we do the same thing with 0, it's the easiest one. Negative e to the 0 would be a negative 1. It's always negative. 0 minus 3 is a negative, but 0 plus 1 is positive. So we have negative, negative, positive. So overall, interval is positive. If we go over here to the 4, always negative in this first factor. This one switches over to being positive. 4 plus 1 is a positive. So our interval here is going to be negative. We are increasing then in the interval from a negative 1 to 3. So our answer would be negative 1 to 3 is when we're going to be increasing. All right. Number 10, same as 7 and 8. This is definitely a calculator question. You would want to take this derivative. You're going to want to set that equal, second derivative, since we want to change in concavity. So you're going to want to take your second derivative. You'll have to graph that, figure out where that crosses the x-axis. Where do you get a sign change? If you wanted to, it's going to be D. Again, you're going to see some graphs here momentarily that we'll be able to have to look at and interpret and read. 11. Here's your function. It says for what value of x is the slope of the line tangent to our function equal to 3. So what this is really just saying is, when is our derivative equal to 3? We'll set it up. This is another one you're going to have to use your calculator to actually answer the question. But if we took our derivative of this, the derivative of this function, we would drop the 2 down. The exponential function would stay the same. And then we've got to do the derivative of the exponent, which is 8x. And then that has to get set equal to 3. So we would get 16x. E to the 4x squared equals a 3. If we were graphing it, you're either doing the intersection of these two, or we would subtract this over and then solve that. If we didn't have the calculator in our hand, because this again can't be on the AP test if you have to graph it and solve it, this should factor nicely like this one did. Even though the number 9 was ugly, it does end up ultimately factoring nicely so that you can set up your sign chart and test all of your answers. Okay. All right, moving along here. Same with 12, calculator question. We would have to graph that, figure out where there's a maximum. That is going to be 0.91, if you want to try that on your own. 13, I'm giving you the second derivative. It's asking where do you have points of inflection. So what we don't want to do, this is just kind of a sucker question in terms of us seeing if you know when you have a point of inflection. This is your second derivative. We don't just want to set that equal to 0 and assume that all of these are going to work, because they don't. We would test them all, so -1, 0, and 2. But when we go through our tests, what do we start with? The -2 would be negative, negative. This is always positive. So we would go positive, and then this should change to negative. This should change to positive, but what you would find is around the x value of 2, we don't get a sign change. It says positive, positive, so that's not going to give us a sign change. So we always want to test those. So we have a point of inflection at -1, point of inflection at 0, so we're going to pick C. All right. 14, again, calculator question. We won't go all the way through it. Just keep in mind, critical points are when your derivative is 0 and when the derivative is undefined. So you would want to graph this, figure out within the interval of 0 to 10, how many times do we cross the x-axis. There is a place where this is undefined. Our derivative is undefined at 0, but since 0 is not in our interval, since it's an open interval, we wouldn't have to worry about that one. So you would just graph that, figure out how many times that changed within the interval. I don't remember what that is. Let me see. Yeah, not sure what that is off the top of my head. So I don't worry too much about that. All right.